Hello students, welcome back to the next module of the chapter Oscillation. In the last module, we saw the conditions under which an oscillatory motion is called as simple harmonic motion. There were two important conditions. The first condition, the force and displacement are in opposite direction. That is, the force is always directed towards the mean position, and the second condition, the magnitude of force is directly proportional to the displacement of the particle. Now, keeping these two conditions in mind, in this module, we will define linear SHM. So, let's start with the definition of linear SHM. So, how can we define linear SHM? So, linear SHM is defined as the linear periodic oscillatory motion of a body in which, point number one, the restoring force or acceleration is always directed towards the mean position. Now, why or acceleration? So, we should know from Newton's second law of motion, F is ma. Since m is constant, F is proportional to a. Therefore, force and acceleration are always in the same direction. And the second point, the magnitude of the force is directly proportional to displacement of the particle from its mean position. So, while defining linear SHM, we should clearly remember these 2 points. Next, so mathematically this can be expressed as F is proportional to minus x. Proportionality sign is removed by constant k, which we have already seen in the last module. So, I can write it as F is equal to minus kx, where k is a constant called as force constant. In magnitude, I can write F is equal to kx, and hence force constant k can be written as F upon x. Let's define force constant. Since k is F by x, F is restoring force, x is displacement. Therefore, force constant is defined as restoring force per unit displacement. Let's go for its SI unit. So, I can write SI unit as formula of k is F by x. Unit of force is Newton, displacement unit is meter, and hence SI unit of force constant k is Newton per meter. CGS unit will be dyne per centimeter. Let's write the dimensions of force constant. So, dimensions of force constant will be the dimensions of force F upon dimensions of displacement. Students, we have already studied in 11th standard measurement chapter the dimensions of force. So, dimensions of force are m raised to 1, l raised to 1 and t raised to minus 2, and dimensions of displacement are m raised to 0, l raised to 1 and t raised to 0. Dimensions of L can cancel, and hence dimensions of K are m raised to 1, L raised to 0 and t raised to minus 2. Let's write some important points for entrance. So, can I say, students, all linear simple harmonic motions are oscillatory? Yes, we saw in the definition only. Linear SHM is linear periodic oscillatory motion. So, all linear SHMs have to be oscillatory in nature. Let's go for an example. Say block attached to a spring mass system. Is it oscillatory? Yes, it is oscillatory. It is performing to and fro motion. Is it linear SHM? Yes, we have already defined this. It is linear SHM. Let's take another example. Say a simple pendulum performing a to and fro motion. So, is it oscillatory in nature? Yes, it is oscillatory in nature. If that amplitude is very small, then it is also performing a linear simple harmonic motion. So, I can say in both the examples, they are oscillatory, they are linear SHM as well. So, all linear SHMs are oscillatory motion. But are all oscillatory motions linear simple harmonic motion? So, answer is no. So, all oscillatory motions are not linear simple harmonic. For an example, say a ball dropped from a height and strikes a floor. Let us assume the collision is perfectly elastic. So, as a result, the ball will bounce between 2 points. It is performing a to and fro motion. So, yes, it is oscillatory in nature. But is it a linear SHM? The answer is no. As we know, the force acting on the block is its weight, which is gravitational force, And in oscillation we have studied for very small heights this magnitude of force remains constant. That means it is not proportional to x, it is independent of x, it remains constant. So the ball is performing oscillatory motion, but this is not a linear SHM. Let's take another example, student. A ball kept on a curved surface. You can see it's moving to and fro. So yes, is it oscillatory? Yes, the motion is oscillatory. Path is not a straight line. Also the conditions of force proportional to x are not obeyed here. So it is not performing a linear SHM. So I can say in both examples they were oscillatory but not linear SHMs. So I can conclude all linear SHMs are oscillatory, but all oscillatory motions are not linear SHMs. Very important point for entrance students. That's all in this module, students. See you in the next module.